Hello everyone, I'm Joseph Lau, a third-year physics undergraduate student at UCLA. My talk today will be about a modern reassessment on the feasibility of neutrino communications. My research advisor is Professor Jay Hauser at UCLA, whose guidance has been instrumental throughout this entire process. In this talk, I'll be examining whether neutrino beams can realistically carry information for feasible communication. To do so, I will contrast two seminal results: Huber's 2010 paper, arguing that neutrino communication can be feasible using muon decay neutrino factory, the front end of a muon collider, and Haapanen's 2003 paper, arguing that it is infeasible with conventional pion decay neutrino beamlines. The listed universities are their affiliations at the time. Here's the roadmap for this talk. I'll begin with a brief intuitive outline of the two sources: conventional pion decay neutrino beamlines and muon decay neutrino factories that come from the front end of a muon collider. Then I'll walk through the key physical processes and parameters that control detection. With that in hand, I will build the signal rate and pulse position modulation capacity framework, including what power and energy per bit that it would take. Finally, I will compare today's and near future beamlines to neutrino factory and showcase what that means for modern neutrino communication feasibility. In this slide, I highlight the decay chains that powers all of the communication scenarios. A high-energy proton beam hits a target and produces charged pions. Those pions decay into a muon and a neutrino. In Haapanen's pion decay neutrino beamlines, we stop here for the source. The focused pions decay into a conventional neutrino beam. In Huber's neutrino factory scheme, the muons from pion decay are captured, cooled, and stored in a ring. The stored muons then decay, given by this second process here, and these decays in the long straight section of the ring, which makes the intense and tightly collimated neutrino beams that are used for communication. Note that for neutrino versus antineutrino beams, although the two sources contains both beams, the respective cross sections only differ by a factor of 2. So choosing the neutrino beam, which has higher cross section, does not change the overall feasibility conclusions. And the feasible communication criteria is to achieve an information capacity C of 1 to 100 bits per second, which I will explain later on. So for pion decay neutrino beamlines, we have a high power proton beam that produces pions and kaons that are then focused by magnetic horns before decaying into neutrinos. The key geometric limiter here is this beam divergence angle, theta naught. It is defined as the ratio between the transverse pion momentum and the longitudinal pion momentum. Since PT here is fixed at around 0.5 GeV by magnetic horn focusing, a higher longitudinal momentum, PL, leading to higher energy, means a smaller beam divergence angle and greater on-axis flux. This figure here shows the K2K's beamline of two magnetic horns when a 12 GeV proton beam strikes the target. The two magnetic horns select and focus the pions into a long decay region. The focused pions decay into muons and neutrinos, and the muons are largely removed downstream, while the neutrinos continue along the beam axis towards the far detector. Muon colliders are highly sought after because muons radiate far less synchrotron radiation than electrons, allowing for compact multi-TeV center of mass energy rings with clean point-like collisions. The challenging part, however, is the very short lifetime of the muon of around 2.2 microseconds, as the collider must capture muons from pion decay, bunch them, cool them rapidly via ionization cooling, which is very important, and then accelerate them rapidly to very high energies in the storage ring. That chain demands very strong magnets and deals with intense neutrino radiation. The key design is tuned to maximize luminosity at the interaction point. A neutrino factory is essentially the muon collider front end, but at tens of GeV instead of TeV. After the proton target stage producing pions, we capture the resulting muons, bunch them in RF cavities, accelerate them to a stored muon energy, E0, and then inject them into a storage ring. The long straight sections are really crucial. They point the muon decay neutrino beam at far distant detectors. This beam divergence angle, theta naught, for neutrino factories are defined by the mass of the muon divided by the muon stored energy, which is also the inverse of gamma. So therefore, a higher energy, E naught, will lead to a smaller theta naught and area, which means a more concentrated flux on the detector, and this will boost detection rates, which is instrumental in enhancing communication feasibility overall. A critical process in which muon detection is viable in non-vacuum mediums arises from converting a charge current interaction, given by this process, into measurable photons from a muon traveling in some medium. N is a nucleon in the medium, and X are the hadronic remnants, where this interaction is known as inclusive neutrino scattering. This slide highlights the interaction probability via the cross-section. In the 10 to 100 GeV band that we're focusing on, the charge current neutrino cross-section is well approximated by this equation here, with the antineutrino cross-section roughly half as large. These very small numbers, as you can see from the 10 to the minus 38 order of magnitude, quantify exactly why neutrino interactions are so rare, which is why feasible rates require really large effective areas and large muon tracks. The energy relation between the neutrino and the secondary muon is described by the inelasticity, Y. The typical secondary muon only gets around 40 to 60% of the incident neutrino energy. When a neutrino interacts, it produces a secondary muon that propagates through water and emits Cherenkov light. It is this muon track and its photons that we can actually detect. When its speed exceeds c over n, it would emit Cherenkov light on a cone of angle theta c, given approximately by this equation here. Next, the TAM formula for Cherenkov light tells us how many photons are produced per unit track length in a given wavelength band, from lambda 1 to lambda 2. Then, accounting for geometry and attenuation, a PMT of area A at distance r only intercepts a fraction of the cone, and the light is exponentially absorbed over the optical absorption length, lambda ABS. There is also a threshold where the resulting N gamma lets us define the maximum detectable muon track distance, where we still expect at least NT photoelectrons. Here, I'm summarizing how far the secondary muon travels in water. The muon's average range, r mu in water, obeys this equation here, which is the particle data's group continuous slowing down approximation, or CSDA, which is a method for calculating the average path length of a charged particle as it slows down and stops in a medium. In our energy range of 10 to 150 GeV, we can approximate the stopping power coefficients, where A is ionization and Be covers radiative losses. Integrating this gives a logarithmic expression for the muon range R mu in meters. Over this energy range, it's mostly linear, and it can also be numerically fitted as R mu as 14.5 plus 3.4 E mu per GeV. Longer tracks increase the chance to pass within RT of a sensor, and this is exactly what enlarges the effective detection area. The muon can pass by near many sensors before stopping, which boosts the detection probability. And a brief note on the secondary muon track reconstruction. They are essential and critical for decoding the faint signal and rejecting or filtering out background noise. For example, if the reconstructed detected secondary muon track is observed to trace exactly back to the original transmitter, then it's part of the signal. Otherwise, it can be discarded as noise. This slide translates the neutrino factory storage ring picture into an explicit flux. The top formula is the standard on-axis neutrino spectrum from decays of unpolarized muons with energy E0 in a straight section at distance L. And you can see the E0 squared over L squared geometric scaling and the detailed energy dependence in the brackets. To estimate an actual detection rate, we combine this spectrum with the inclusive charge current cross-section and the muon range in a medium, which gives the secondary muon flux in the second line. This muon flux is what enters the detection rate integral and the information capacity calculation. This is the rate law that ties the whole system together. The detected muon rate is an integral over neutrino energy for three factors: the charge current cross-section, the detection probability, and the neutrino flux from the source. In the GeV regime, we have the cross-sectional proportional to the neutrino energy, the detection probability proportional to the range proportional to the energy, and the neutrino flux proportional to n mu epsilon E naught squared over L squared. And putting all these together gives a very steep signal rate proportional to n mu E naught to the 4 over L squared multiplied by the straight section fraction and the effective detection area, which is pi RT squared. This E naught to the 4 scaling is the primary reason why a high energy neutrino factory looks so much more promising than the pion decay neutrino beam, which only has an E to the squared scaling dependence from the cross-section and the detection probability, lacking the neutrino factory's beam collimation gamma squared factor. This difference is ultimately the key driving force in the overall feasibility landscape. To turn rare neutrino events into a feasible communication channel, we use pulse position modulation, PPM, in information theory. PPM is a method of transmitting information or signal modulation by shifting the position of a pulse within a fixed time frame. We chop time into m slots per frame and choose which slots to send a pulse in, where m is also the inverse of the duty cycle. If none of the pulses B produce a count, the whole symbol is erased, with an erasure probability per pulse that falls exponentially as the total signal rate S increases. The first expression on top is the exact capacity C as a function of P. Optimizing over P for a given muon detection rate S, the expected muon events per second at the receiver, a maximum CS function, i.e. the maximum reliable information rate, can be found for the specific m equals to the 14, corresponding to a duty cycle of 10 to the minus 4. The capacity is empirically well fit by 6.61 times S to the power of 0.74. Now we have obtained the C of S function, which is the keynote quantity of determining feasibility. Generalizing Hubert's numerical fit, I now derive a more rigorous expression that keeps track of how capacity depends on both the event rate S and the number of slots M. The key step is introducing a dimensionless parameter Y, which is a ratio of P over S. That measures how heavily we load each frame with pulses. From the first equation, optimizing the capacity over P results in this transcendental equation for Y, and once we solve it, we can get an approximation for C of S. When M is much greater than S, the capacity is roughly linear in S. And also, if P is less than S, most detected events do not have a unique slot, so there are many leftover slots. If P is greater than S, many transmitted pulses land in the same slots, leading to pileup. To overcome this issue, we choose optimality of Y as 1. At large S, the behavior crosses over to the sublinear power law function seen in Hubert's fit previously. Crucially, an increase in S corresponds to a linear increase in C, while an increase in M only corresponds to a logarithmic increase in C, implying that no matter how good the modulation or how large the M value is, the rate must still be high for sufficient capacity. The top table emphasizes the significance of higher energies in the neutrino factory, as increasing E naught from 10 to 150 GeV boosts the event rate S by a factor of roughly 5 times 10 to the 4, which is very, very large, holding all other parameters constant. Next, comparing with pion decay beamlines, the lower table then compares Minos and K2K to the factory, which has rates of around 2.2 per second and capacity of 10 bits per second. This huge gap in C and S between the two sources of around order 10 to the 5 to 10 to the 6 magnitude is a major reason why neutrino factories look feasible for communication and pion decay beamlines do not. Once we know the event rate and the information capacity, we can define an energy per bit, which is the wall plug power divided by the capacity. For pion decay beamlines such as Minos and K2K, that cost is enormous, requiring around 10 to the 9 to 10 to the 10 joules per bit. The neutrino factory brings that down roughly to 10 to the 6 joules per bit, a few orders of magnitude better, but still very energy hungry. Even modern high-power beamline like Nova with 0.7 megawatts of beam power improves this by less than an order of magnitude. Despite neutrino factories drawing significantly more power than pion decay beamlines, they are vastly more energy efficient for communication. Additionally, both the beam power and the corresponding energy per bit are crucial physical design limitations for feasible neutrino communication. Up to now, neutrino factories and muon colliders are still purely theoretical design studies. However, what we do have are pion decay beamlines. So the question really leads to, how far can we push them as neutrino communication channels using the same rate and ppm capacity framework? Given the beam power, we can estimate their maximums S and C, translating that into energy per bit. However, modern pion decay beamlines remains order of magnitude below a neutrino factory, so neutrino communication is unfortunately not yet practical, feasible, nor competitive. This slide computes modern-day pion decay beamlines using the ppm capacity model, Hyper-K and T2K, and Dune and Nova. Interestingly, a 2012 demo by Fermilab showed that neutrino communication over a very short baseline of 1 kilometer was possible, but only at low capacities near 0.1 bits per second. And a caveat worth mentioning is that most of these beamlines aren't uniquely optimized for high neutrino energies. Based on this, I fixed their non-energy parameters and scaled their energies upward to see where they would enter the feasible range. More detailed values are also available in the backup. To understand what approximate energies and rates current pion decay beamlines require to reach the feasibility window, this slide shows just how difficult it is to obtain a usable 1 bit per second, even with more optimistic M values chosen. The upper rows are the current peak neutrino energies and rates, while the middle rows give the required rates for 1 bit per second, and similarly for energy below. Minos and K2K would need rate energies of 10 to the 3 to 10 to the 5 orders of magnitude and neutrino energies of 60 to 300 times higher, which is currently unrealistic. T2K is marginally better, but still requires huge energy boosts. In contrast, a 50 GeV neutrino factory is already near 1 bits per second, needing only around a 1.3 times energy increase. Hence, existing pion decay beamlines are still far outside the feasibility window. Therefore, if we want to reach the minimum feasible regime of 1 bit per second, only high-energy muon decay facilities come close. Optimistic neutrino factories with around E naught greater than 60 GeV can reach this range at Earth diameter baselines. In contrast, existing and future pion decay beamlines are still 3 to 5 orders of magnitude below that, even after scaling up their neutrino energies. The core reason stems from the missing E naught squared factors from acceleration, collimation, and straight section in the factory. To conclude, neutrino beam communication remains an extremely power-intensive and costly channel that, although scientifically feasible with neutrino factory sources, it is by far not yet competitive with conventional communications in terms of information capacity. I am grateful for the invaluable support and guidance from Professor J. Hauser at UCLA, and thank you so much for listening, and I look forward to the upcoming discussions.